So let's solve problem 3 from worksheet 0328. So what we have here is technically called a deleted disk. So it's like a circle with a smaller circle subtracted from the middle. So from this region, which is from A to 2A in radius, so this middle region is empty, and then from radius A out to radius 2A, we have a total current I out of the board, and that current is uniformly distributed across the area of this deleted disk. So then we want to know what is the magnetic field in this region R less than A, and then what is the magnetic field in this region between A and 2A, and what is the magnetic field in this region outside of 2A. So since the current is out of the board, we can use this right-hand rule, this is actually my right hand, to get that the magnetic field lines must be counterclockwise like this. And they encircle the current, and the magnetic field should be constant for a constant radius. Magnetic field should only be a function of radius because of the cylindrical symmetry of the problem. So this is our magnetic field. It's going to be tangential clockwise, tangential anti-clockwise, tangential counterclockwise. Okay, so now we can evaluate the magnetic field using three different Ampere's law loops. Let's first do a loop that goes around here for the region R less than A. So if we have R less than A, so by symmetry, the magnetic field depends only on the radius. It doesn't depend on this azimuthal angle, and it also doesn't depend on the coordinate z along the axis. You know, normally I would call this y and this x, and I would say that z is pointing out of the board. So 2 pi rb, that's the same thing as this line integral of b dot dl, but you see we just went around a circle, so the distance we went was 2 pi r, and I just multiplied by the magnitude of b because my little Ampere loop is always parallel to the magnetic field. So if there were any magnetic field lines, they would be counterclockwise circles. But this equals mu naught times the current enclosed by my loop. So here's my purple loop. And notice there is no current inside there because all the current is between A and 2A. So this is actually 0. So as long as symmetry imposes the condition that the magnetic field is the same everywhere on this loop, then that value, which is the same everywhere, must be 0. So you can see that b equals 0 is the solution here for R less than A, because there's no enclosed current. Okay, so I mean you would get, you know, the magnitude of b is mu naught I enclosed over 2 pi r, but I enclosed is 0. So then b is 0 in this R less than A region. So then let's do a more interesting, well actually let's next do R bigger than 2A. How about that? So R bigger than 2A. So now our Ampere's law path is going to be out here like this. Okay. And so that's our loop, but I claim that our loop is just following a single magnetic field line, because the magnetic field lines have to be a function only of radius, and they have to be counterclockwise since the current is out of the plane of the board. And the magnetic field lines are, the magnetic field magnitude is only a function of radius because of the cylindrical symmetry of the current distribution. So then this integral b dot dl again just takes the form 2 pi r times b, because our little path dl is everywhere parallel to the hypothetical magnetic field lines B. So that dot product is just multiplying the two magnitudes, and the cosine theta factor between the B field and the dl is just 1. So this is mu naught I enclosed. So this is easy because the total enclosed current is 1. Sorry, is I. The total enclosed current is I. So that's mu naught I. Here's our total current I. So that gives us that B is mu naught I over 2 pi r. That's the same thing you would get for just a single straight infinite wire carrying current I. And the direction is, you know, tangential counterclockwise. Okay. That's fine. So the tricky part is for r between a and 2a. So if we do a is less than r is less than 2a, then the trick is, so here let's just go along this one field line here. So we'll call this radius r. Then once again we just have 2 pi r B, because we picked our Ampere's law loop for the line integral just to be along a single magnetic field line. So that dot product is just the dl of the arc length, dot product with B. That's just the magnitude of the arc length times the magnetic field magnitude. Since the two vectors are parallel. So this is mu naught times I enclosed. Now, this is a little bit trickier. What is I enclosed for that region in between? So I claim that for a less than r less than 2a, I enclosed is I times the area of the deleted disk from A up to R divided by the area of the deleted disk from A up to 2A. You see, it's just, the question is just what fraction of the current do I enclose? And that's the same question as what fraction of the area do I enclose? And so it's the area of this smaller deleted disk. It's like the area of this shaded region divided by the area of this original region that carries the whole current. So the area of a deleted disk so like R1 to R2 is going to be, so the area of the big circle is pi R2 squared, but then you subtract out the area of the small circle, so that's pi R1 squared. You see, you have like a big circle with like a small circle deleted from it. So you take the area of the big circle, pi R2 squared, and you subtract the area of the small circle, pi R1 squared. So that's pi, you know, R2 squared minus R1 squared. Okay, so then we can just apply that here. And so this seems to be mu naught. Now the factor pi is going to cancel. I'll write it anyway just for fun, but it's going to cancel out. So this deleted disk from A to R. So this is R squared minus A squared. And then here is pi. The pi will cancel. This is 2A squared minus A squared. Okay. Oh, times I. This is the original I. Okay. So this equals mu naught I times r squared minus a squared, and then this is, okay, 4a squared minus a squared is just 3a squared. So I think this is fine. This equals 2 pi rb. So that then gives us, that the magnetic field B has magnitude mu naught I over 2 pi r times r squared minus a squared over 3a squared. If you want to clean it up by factoring, you could. I'm not sure it's worth the hassle. Mu naught I over 6 pi a squared r squared minus a squared is one way you could do it. Another way you could do it I think we could make this like 1 minus, we could make this, yeah, I guess we could divide out the a squared and make this term be 1. Let's see how that looks. So then we could say mu naught I over 6 pi r. So that looks like a magnetic field. And then this is r squared over a squared minus 1. I guess that's kind of nice. And then, again, it is, you know, tangential and counterclockwise. Let me just compare with my pre-computed answer. Well, I actually left it in this form. So I said mu naught I over 2 pi r squared minus a squared over 3a squared. Okay, but I guess this version looks a little nicer.